Hey there, ready to dive into a math mystery, one that puzzled the greatest minds for centuries.
Oh, yeah.
Buckle up, because today we're tackling Fermat's last theorem.
It's a theorem that's, easy to grasp,
Yeah,
but notoriously difficult to prove.
exactly. And it all started with a simple note,
Right.
scribbled in the margin of a book.
A famous margin note.
Our source for this deep dive
Yes.
is this fascinating YouTube video
Okay.
from Ciência.
Interesting.
It's a Brazilian science channel.
Oh, wow.
The title is Último Teorema de Fermat, o mais difícil da matemática,
Okay.
which translates to Fermat's last theorem, the hardest in math.
Catchy.
So let's find out how challenging it really was.
Well, imagine this. Back in 1637,
Okay.
Pierre de Fermat,
Yeah.
a lawyer and amateur mathematician,
Interesting.
was reading an ancient Greek text about Pythagorean triples.
Right.
Those sets of numbers that satisfy the famous equation.
Yep.
A squared plus b squared equals c squared.
Right, the foundation of geometry.
Exactly.
So what sparked Fermat's interest in all of this?
Well, he started wondering if this neat relationship between squares could be extended to higher powers.
Okay.
Could you split a cube into two other cubes?
Uh-huh.
A fourth power into two fourth powers, and so on.
Okay.
Fermat concluded that, nope, this kind of perfect split
Yeah.
was impossible for powers greater than 2.
Okay, so he figures this out.
Right.
But what makes it such a big deal?
Here's the kicker.
Okay.
He jotted down this idea in the margin of his book,
Right.
claiming to have a proof, but saying there wasn't enough space to write it out.
Oh, wow.
Talk about a cliffhanger.
That's one way to leave your mark on history.
Definitely.
So what happened next? Did anyone believe him?
Well, that tantalizing little note
Yeah.
became the most famous margin note in history,
Wow.
sparking a mathematical treasure hunt
Okay.
that lasted over 350 years.
Oh, my gosh.
Generations of brilliant minds tried to find Fermat's elusive proof.
Right.
And while they made some progress, the complete solution
Yeah.
remained out of reach.
It sounds like a real head-scratcher.
It was.
What kind of progress did they make if they couldn't find the complete proof?
Well, Fermat himself actually proved a specific case of the theorem
Okay.
for the power of 4
Okay.
using a technique called infinite descent.
Infinite descent.
Yeah.
That sounds intense. Can you break that down for us?
Absolutely. Imagine you're trying to prove something is impossible.
Okay.
You start by assuming it is possible.
Right.
Then you show that this assumption leads to a logical contradiction.
Okay.
You demonstrate that if the thing were possible,
Yeah.
you could create an even smaller example of the same thing,
Right.
and then an even smaller one,
Oh.
creating an endless chain of decreasing numbers.
So it's like saying if I can jump this high,
Yeah,
then I can jump half as high and then half of that and so on forever.
exactly. But in mathematics,
Right.
there's a limit to how small whole numbers can get. You can't have an infinitely decreasing sequence of them.
Oh, I see.
This means the original assumption
Yeah.
that the thing was possible in the first place
Right.
must have been wrong.
Okay.
That's the power of infinite descent.
Wow. That's a clever way to prove something impossible.
It is, yeah.
So Fermat tackled the power of 4.
Right.
Did others pick up where he left off?
They sure did.
Oh.
Another brilliant mathematician, Euler,
Yeah.
proved the case for the power of 3.
Okay.
And then mathematicians realized they could streamline the problem.
Oh.
If they could prove the theorem just for prime numbers,
Okay.
it would automatically apply to all other numbers as well.
Ah, so they found a shortcut by focusing on the building blocks of numbers.
Exactly.
But I'm guessing even with prime numbers, it still wasn't a walk in the park.
You're right about that. This is where Ernst Kummer and his work on regular and irregular primes comes in.
Okay.
He managed to prove Fermat's last theorem
Uh-huh.
for regular primes.
Right.
But those pesky irregular primes
Yeah.
kept popping up and causing all sorts of trouble.
So it's like finally finding the right path,
Yeah,
only to discover there's a detour.
kind of, yeah.
What was the issue with irregular primes?
Well, Kummer's method, which worked beautifully for regular primes,
Right.
simply didn't apply to irregular primes.
Okay.
It's like having a key that fits most locks,
Mm-hmm.
but then you encounter this strange lock that requires,
Right.
a completely different approach.
Yeah. Okay.
And to make things even more challenging,
Oh, no.
it turns out there are infinitely many irregular primes.
So even with this shortcut
Right.
and Kummer's progress,
Yeah.
Fermat's last theorem remained elusive.
It did.
That must have been frustrating for mathematicians.
It was.
What were they to do?
Well, at this point, some began to wonder if Fermat's last theorem was simply impossible to prove, even if it was true.
Okay.
And this brings us to another fascinating concept, Gödel's incompleteness theorems.
Now, those sound intimidating.
They are quite profound.
Okay.
But bear with me.
All right.
Gödel showed that within any formal system of mathematics, there will always be true statements that can't be proven within that system.
Wait, so you're saying there could be mathematical truths that are true but impossible to prove?
Exactly.
How can that be?
It's a mind-bending idea, isn't it?
Yeah.
This raised the unsettling possibility that Fermat's last theorem might be one of these untouchable truths.
Okay.
Forever true, but eternally unprovable.
So was this the end of the road for Fermat's last theorem?
Not at all.
Okay.
In fact, a wealthy German industrialist offered a prize, the Wolfskill Prize, for anyone who could prove Fermat's last theorem.
Wow.
It generated a flood of proofs.
Oh, I bet.
From amateur mathematicians.
I can imagine. Who wouldn't want to claim they'd solved one of math's greatest mysteries?
Right. There's even a story about a famous mathematician, Edmund Landau, who was so inundated with incorrect proofs that he had pre-printed rejection cards made.
Wow, that's dedication. So even with all this attention and effort, the mystery remained unsolved.
It did.
But didn't someone eventually crack the code?
Indeed.
Okay.
And that's where our hero, Andrew Wiles, steps onto the stage.
Okay, so last time we left off with this unsolved mathematical enigma and a whole lot of incorrect proofs floating around.
Yes, Fermat's last theorem had become, almost a legend in the world of mathematics.
And then Andrew Wiles enters the picture.
Exactly.
Tell me about his journey.
Well, Wiles had been fascinated by Fermat's last theorem since he was a child.
Okay.
But as, a serious mathematician, he knew he couldn't dedicate his career to such a seemingly impossible problem.
So what was his strategy? Did he just dive headfirst into Fermat's note and try to decipher it?
Not quite.
Okay.
He realized he needed to approach it indirectly.
Interesting. Okay.
He focused his attention on a seemingly unrelated area of mathematics.
Elliptic curves.
Elliptic curves.
Yeah.
Now, those sound a bit more complex than Pythagorean triples.
They are a little bit, yeah.
What are they exactly?
Well, imagine them as equations that create these beautiful symmetrical curves. You graph them. They have all sorts of intriguing properties and connections to other areas of mathematics.
Okay, so Wiles was working with these elliptic curves.
Yes.
But how did that lead him to Fermat's last theorem?
Right.
The two seem worlds apart.
Well, that's the beauty of this story.
Okay.
It's all about unexpected connections.
Right.
You see, around the same time, there was this other fascinating area of mathematics called modular forms.
Modular forms. All right, now we're getting into the really abstract stuff.
I know, a little bit, yeah. I'm trying to picture that.
Think of them as functions. With incredible symmetry. Even more intricate than elliptic curves.
Right.
They're kind of like mathematical kaleidoscopes.
Oh, wow.
With patterns repeating in complex and beautiful ways.
Mathematical kaleidoscopes, huh?
Yeah.
But what do these modular forms have to do with Wiles' work on elliptic curves?
Well, back in the mid-20th century, two Japanese mathematicians, Yutaka Taniyama and Goro Shimura, proposed this radical idea.
Right.
They conjectured that elliptic curves and modular forms were actually deeply connected. Two sides of the same coin.
Wow. So they thought these completely different mathematical objects were somehow linked at a fundamental level.
Yeah.
That's a pretty bold idea.
It was a revolutionary concept. If true, this connection, known as the Taniyama-Shimura conjecture, would unlock a whole new set of mathematical tools and insights.
So it was a huge deal.
It is.
But also incredibly difficult to prove, right?
Absolutely. For decades, mathematicians struggled to prove this conjecture.
Right.
It seemed almost too good to be true.
So while mathematicians were grappling with this conjecture, Wiles was off working on elliptic curves, seemingly unaware of how this all tied together.
That's right. Then another mathematician, Ken Rabet, made a groundbreaking discovery. He proved that if the Taniyama-Shimura conjecture was true, then Fermat's last theorem had to be true as well.
Whoa, hold on.
Yeah.
So proving this link between elliptic curves and modular forms would automatically solve Fermat's last theorem.
Yes.
Talk about a domino effect.
It was a game changer.
Right.
Finally, Wiles had a respectable problem to work on.
Okay.
Proving Taniyama-Shimura. That might indirectly solve the seemingly unsolvable Fermat's last theorem.
This is starting to sound like a mathematical thriller.
A little bit, yeah.
We've got centuries of dead ends, this seemingly impossible conjecture, and now this surprising connection that could unlock everything.
Exactly.
So what did she do?
Well, Wiles decided to take on this challenge in secret.
Oh, really?
For 7 years, he worked tirelessly in isolation.
Wow.
Only sharing his progress with a trusted colleague.
Okay.
When absolutely necessary.
7 years.
Yeah.
That's longer than some people spend getting a PhD. Talk about dedication.
It is, yeah.
Why all the secrecy?
Well, the pressure was immense.
Right.
He knew that if word got out that he was working on Fermat's last theorem, the expectations and scrutiny would be overwhelming.
Yeah.
He needed a quiet space to explore these complex ideas without the weight of the world on his shoulders.
I can only imagine the pressure.
Yeah.
It's like trying to solve a Rubik's Cube blindfolded while everyone's watching you.
Exactly.
So Wiles chose to work in solitude, meticulously building his proof step by step.
Step by step.
And after all that time, did he finally crack it?
Well, in 1993, after years of intense work, Wiles emerged from his mathematical seclusion. And presented his findings at a series of lectures.
Oh, wow.
The lecture hall was packed.
I bet.
With mathematicians from all over the world.
Wow.
Eager to hear what he had discovered.
This must have been like the Olympics of mathematics.
In a way, yeah.
What was the atmosphere like?
Oh, you could feel the anticipation in the air.
Yeah.
At the end of his final lecture, Wiles dropped the bombshell.
Right.
He announced that he had proven a special case of the Taniyama-Shimura conjecture.
Right.
And thanks to Ribet's work, that meant Fermat's last theorem was true.
Wow, what a moment.
It was.
I can only imagine the excitement and applause in that room.
There was a lot of it, yes.
It was a triumph.
It was.
Or so they thought.
Right.
Shortly after the celebrations died down. A flaw was discovered in Wiles's proof.
Uh-oh.
Oh, no. What a devastating setback.
It was.
After all that work, to have it fall apart at the last moment.
It was a crushing blow for Wiles.
Yeah.
But instead of giving up, he went back to work.
Good for him.
Determined to fix the error.
Okay.
This time, he wasn't alone.
Oh.
He collaborated with a former student, Richard Taylor.
Okay.
And together they wrestled with the problem for over a year.
So it's like the sequel to the mathematical thriller.
Right.
Fermat's Last Theorem, The Comeback.
Exactly. And this sequel had a happy ending.
Okay, good.
In 1995,
all right,
Wiles and Taylor published a revised and corrected proof.
Okay.
Finally putting Fermat's last theorem to rest.
Wow.
After more than 350 years.
What an incredible story of perseverance.
It is.
Not only did he solve one of the biggest math puzzles ever.
Yeah.
But he overcame a major setback to do it.
He did.
But wait, didn't I hear something about Wiles missing out on a major award?
Yes.
Because of this delay.
You're right. Sadly, Wiles missed the cutoff age.
Oh, no.
For the Fields Medal.
Right.
One of the most prestigious awards in mathematics. By just a few years.
Oh, wow.
It's only awarded to mathematicians under the age of 40.
Okay.
And Wiles turned 40 before his corrected proof was formally accepted.
Yeah, what bad luck.
I know.
But I suppose proving Fermat's last theorem is its own reward.
Absolutely.
And his work must have had a huge impact.
It did.
On the world of mathematics, right?
Absolutely. It wasn't just about solving a centuries-old puzzle. His proof opened up entirely new avenues of research.
Okay.
In both elliptic curves and modular forms.
So this seemingly simple margin note sparked centuries of mathematical discovery, culminating in this groundbreaking proof that connected different fields of mathematics in ways no one had imagined before. It's amazing how one little note could lead to all of that.
It is. But there's still one lingering question that continues to intrigue mathematicians and historians alike.
Okay, here we go. The conspiracy theory part of our deep dive.
Not quite a conspiracy, but a fascinating thought experiment.
Right.
Remember, Fermat claimed he had a proof all those years ago, but never wrote it down.
Right.
Could he really have had a proof?
Yeah.
Given the mathematical tools available at the time?
Right.
And if so, what kind of proof could it have been?
It's kind of like a historical whodunit, but for math.
Exactly. We know the theorem is true, thanks to Wiles.
Right.
But could Fermat have had a different, perhaps simpler proof all those years ago?
What are some of the theories out there about Fermat's potential proof?
Well, some mathematicians speculate that Fermat might have stumbled upon a more elegant approach that we haven't rediscovered yet.
Simpler than Wiles' proof, which is over 100 pages long. That's hard to imagine.
I know, right?
Yeah.
But mathematics has a history of surprising us.
Right.
Sometimes the most profound truths have a way of hiding in plain sight.
Maybe Fermat had a unique way of visualizing numbers or relationships.
It's possible.
That allowed him to see a pattern we've missed.
Yeah, he was working with, the mathematical tools available to him in the 17th century.
Right.
Long before concepts like elliptic curves and modular forms were developed.
So no fancy mathematical kaleidoscopes back then.
Exactly.
If he did have a proof, it would have had to be something entirely different.
It would have had to have been, yeah.
That's what makes this so intriguing.
It is.
It challenges our assumptions about what constitutes a valid mathematical proof.
Absolutely.
And reminds us that mathematical understanding is constantly evolving.
It is.
It's like trying to imagine a composer from the Renaissance writing a symphony for electric guitar.
Yeah.
The instrument didn't exist yet.
Exactly.
Fermat's potential proof might have relied on a level of mathematical intuition that we haven't been able to replicate.
Potentially, yeah.
So even though Fermat's last theorem has been definitively solved, there's still this element of mystery surrounding it.
Absolutely. It's a testament to the enduring power of mathematical curiosity.
Right.
Fermat's simple note in the margin of a book sparked centuries of exploration and discovery.
Wow.
It pushed mathematicians to develop new tools, explore new concepts, and ultimately make connections that revolutionize our understanding of number theory.
And who knows what other mathematical mysteries are still out there waiting to be uncovered.
I'm sure there are many.
This deep dive has been an incredible journey.
It has.
We started with a seemingly simple margin note.
Yeah.
And ended up exploring the evolution of mathematical thought over centuries.
It's amazing.
It's a reminder that even the most challenging problems can eventually be solved.
Yeah.
But the journey of discovery is just as important as the destination.
Absolutely.
And who knows? Maybe someday someone will stumble upon Fermat's lost proof.
Maybe.
Revealing a whole new level of mathematical insight.
That would be amazing.
To our listener, we leave you with this final thought.
All right.
What other mathematical mysteries are out there waiting to be discovered? And will you be the one to unravel them?
Ooh.
Keep that curiosity alive. And you never know what amazing insights you might uncover.
You never know.
Happy exploring.
Happy exploring.